All right. By the end of this lesson, you will be able to add and subtract vectors in one dimension. Check, we've already done that. Identify what forces are acting on an object and draw the corresponding free body diagram. Determine if the total force acting on the object is equal to 0 or not, and write a mathematical expression describing the forces and the motion of the object. A lot to do today. In hindsight, I should have given you a pre-quiz over this, because I do a lot of talking. Sorry. So get out some notes. We've busted through that already. Now we're going to start identifying different types of forces. We haven't really, up until this point, we just said, yeah, it's a force. But there are specific types of forces. Okay. First off, you've got the force of gravity, which is pretty obvious. Acts always acts straight down. Okay. However, during this chapter, we're just going to focus on forces that are acting in the horizontal direction. So gravity is not going to be one of those forces that we care about this chapter. It does exist. I'm not trying to say it doesn't. I'm just saying we're not going to worry about it right now. We'll pick that up next chapter. Okay. Friction. Okay. This is caused by the roughness between surfaces. Caused by the roughness between surfaces. Okay. And it always acts parallel to the direction, sorry, not to the direction, always parallel to the surface. Always acts parallel to the surface and always acts in the opposite direction of the way the object wants to slip or slide. Always acts in the opposite direction to the way that the object wants to slip or to slide. Always acts in the opposite direction the way the object wants to slip or slide. Always acts in the opposite way to the way the object wants to slip or slide. Here's that. Okay. Oh, here's a detail I need to tell you about. The way that I label forces, the variable for force is a capital F. Okay. But the way I make a distinction is with a subscript. Okay. The exception to that, though, is friction, where it's just a lowercase f. The reason why is because there's going to be more subscripts in like a month or so. Okay. Next up is air resistance, a cousin of friction. Okay, and this is by collisions with air molecules. Okay, collisions with air molecules. Okay. And the direction of that. So if you ever stuck your face outside of a window of a car, that was air resistance smacking your face. Okay. And this always acts in the opposite direction of motion. Always acts in the opposite direction of motion. Good with that? Always acts in the opposite direction of motion. Next up is tension. Tension is a pulling force from a rope, string, cable, yarn, dental floss, something rope-like. Okay, it's always a pulling force from a rope or string. Good with that? Okay. Okay. Caitlin, push me. Push me. Come on. Push. Okay. Can't push with a rope. Okay. You can only pull. Okay. This is only a pulling force. Like the direction it's going is always pulling. Okay. So always pulls parallel to the rope. Always pulls parallel to the rope. Good with that? That's the force of tension. Last one for today is applied force. You know that, I don't know if you all have a drawer in your house that's like the miscellaneous drawer or the catch-all, like you don't know what. Yeah, just throw it in the miscellaneous drawer. That's applied force. Applied force is like, I don't know what you call that. Yeah, just call it applied force. Good enough. So this a lot of times will be a push or pull from an animate object, such as like a person, animal, machine. Okay. Applied force. Good with that? Okay. So those are the forces I'm introducing you to today. And so we're almost going to start applying them. Okay. So net force. Have you ever heard of net gain, like in business, or the net worth of something? So in business, the net gain would be you get some money in from like sales or something, but then you got to pay the material cost, you got to pay your labor force, and then whatever you have left over, that is your net gain. After everything is said and done, that's what you're taking away. Does that make sense? Net force has a similar flavor. Okay, this means the total force. This means adding up all forces, or taking into account all the forces that are acting on the object. Okay? The net force. You ever seen sigma before in math class? This symbol. Okay, stands for the sum of. So, how would you read that expression? Sum of the forces equals 0. Good with that? Now, we're ready to start. Open our minds up a little bit here. So, up until this point, I have only considered scenarios where there's only been one force or no forces acting on an object. Okay? And so we've said Newton's first law says an object at rest will stay at rest if there's no forces acting on the object. Okay? But the reality is it's not just a one force or no forces. There could be multiple forces acting on an object. Think of a situation where there's more than one force acting on an object, but the object still stays at rest. And hopefully you can come up with something. Like, okay, so the idea that forces still act on things, but yet objects still stay at rest. How is that possible? Because the total force, the net force, can still be 0. So, updating Newton's first law of motion. Instead of saying an object at rest will stay at rest, or an object in motion will stay in motion if there's no forces acting on it, we can say if the net force is equal to 0. So, an object at rest will stay at rest if the net force is equal to 0, meaning all forces cancel each other out, or are balanced. You might have heard that expression, are balanced. Meaning that when you add the forces together, they equal 0. They're canceling each other out. So it has the same effect as if there were no forces acting on it, because the forces are canceling each other out. Still forces, but they balance each other. Solid? Okay, and we can say the same thing about the motion part. This one's easy, like this one's harder. A moving object will continue moving at a constant velocity if the sum of the forces are equal to 0. Okay. A moving object will continue moving at a constant velocity if the sum of the forces are equal to 0. Good with that? Okay. We also need to update Newton's second law of motion. That said, we had force is equal to mass times acceleration. That's if there's only one force acting on it. Technically, the net force, the total force, that's equal to mass times acceleration. And so you know how we talked about how force determines the direction of acceleration. Whatever the direction of the force is, that's the same direction as acceleration. That's if there's only one force acting on it. If there's multiple forces acting on it, then the direction of acceleration is the same direction as the total force. After everything's said and done, what's left over, that or whatever the total force, the direction of the total force is the direction of acceleration. Determines the direction of acceleration. Good with that? All right. You got some background information. Let's use it. So we're going to draw free body diagrams. These are diagrams that capture or illustrate the forces that are acting on the object. Not the velocity, acceleration, the distance, don't care about that. All I care about, we take a snapshot of the object and say, at that moment in time, what forces are acting on the object. I don't care what the object is doing. I just care about what forces are acting on the object. Okay, and these forces are caused by objects touching or in physical contact with that other object. So how the world is acting on the object that we're focused on. Okay, I'll post this PowerPoint, but you'll get a better flavor for these rules when we start applying them. Okay. After we draw the free body diagram, we can use that to do some stuff, which I'll talk you through in examples. Okay, so you got this boulder you're trying to move. You take this rope, you tie it around the boulder, and you're feeling pretty Hulk-like, and like, I think I can do this. And like, you start pulling on this boulder, like, and then you realize you're not the Hulk. You're like, it's not going anywhere. So what forces are acting on the boulder during this point in time? Okay, so to draw your free body diagram, typically I just draw a box, represents any type of object I'm drawing, okay? And I put a belly button on that box. Okay, that's where all the forces are going to originate from. Give me like the origin. Okay. So what forces are acting on the boulder? Now, I'll let you know, yes, gravity is definitely acting on the boulder, but for this chapter, all we're focusing on are horizontal forces. Okay, so I'm not worried about gravity. Yes, it exists. Absolutely. Not trying to say it doesn't, but we don't care about it at the moment. Okay. So, what forces are acting on the boulder? What do you think, Ben? Okay. So I'll take the first one first. Friction. Is everybody okay with that idea? Like the thing that's preventing it from moving is friction. To figure out which direction friction is acting on the boulder, pretend like the boulder could start to slide. Which way would it slide? To the right or to the left? Left. So friction always opposes that direction of slipping and sliding. So friction is going to be to the right. So draw an arrow and label that with a lowercase f for friction. Okay. Then the next one is you got a force going to the right. Is that applied force or is that tension? To answer that question, here's the follow-up question. What object is in physical contact with the rock? The rope or the person? Rope. So therefore, it is a force of tension rather than applied force. So you have tension going this way. That, my friends, is the free body diagram for that scenario. Not too bad, yeah? Okay. Now we're going to use that. Okay. We're going to go through these steps here. So this is step one, free body diagram. Step two is pick a positive direction. My suggestion is make the way it's moving positive. Okay. In this scenario, it's at rest, so it doesn't matter. You pick right or left, make that the positive direction. Does not matter. For kicks and giggles, just to mess with you, I'm going to make to the left positive because that's just weird, but it's still legal. Okay. I'm going to make to the left positive, the right negative. That was step two. Step three, this is probably, this right here is the most important, the most problematic. We're asking ourselves, is the sum of the forces equal to 0? Now, we are not going to look at the free body diagram to discern that unless you're given numbers for that, which you probably won't be. Okay. What you're going to do to look at to discern this is you're going to look at how the object is moving. You're going to look at the motion. Okay. Is the sum of the forces equal to 0? To determine that, you're going to ask yourself, is inertia doing what it wants to do? Is inertia happy? If an object is at rest, is it staying at rest? Is an object moving? Is it continuing to move at a constant velocity? If the answer is yes to those questions, either of those questions, then you can say yes, the sum of the forces are equal to 0 because inertia is doing what it wants to do. It is happy. The total force is 0. They cancel each other out. That's how you know. Okay? So tell your neighbor, is the sum of the forces equal to 0 in this scenario, and tell them why. Okay. Correct answer is Yes. Sum of the forces equals 0. It's at rest and staying at rest. So next step is we are going to find the sum of the forces. We're going to add the forces together. Okay? What forces are acting? We've got tension and friction, but you also need to take into account direction. Okay? So I've got tension and I'm adding that to friction, but I need to incorporate direction. Tension, is that going in the positive or negative direction? Positive. Is friction going in the positive or negative direction? Negative. Okay, I'm adding up all the forces. I'm finding the sum of the forces. What's another way I can write this mathematically? There it is. Tension minus friction. That is the sum of the forces. Okay. Do we know what it's equal to? We've established that that's equal to 0. That's step 5. Okay. So we add up, we take an inventory of all the forces, we add them up, but keep in account direction, and then we set up equal to whatever it's equal to. In this case, it's equal to 0. That, my friends, is your setup. That is way more powerful than you realize at this moment in time. I guarantee it. Okay? So, once you have set up your problem with your free body diagram, then I can say, okay, let's say you're pulling this rock with 100 newtons. How much friction is there? Like, well, 100 newtons, looking for friction. Hey, that's like 100! Because you solve for lowercase f. Ta-da! Easy peasy. Okay, now, does that make sense? So you're going for the setup. I know it's kind of easy, but they're going to get way harder in the future. But like I'm starting you out easy. Okay, good with that? That's those 5 steps we just went through. Okay, next scenario. Let's say I'm kicking a box, and while my foot is in contact with the box, okay, while my foot is in contact with the box, what is the free body diagram? What are the forces acting on the box? Go. Oh, I need to tell you this. This is really important. Here's your default setting. Always include friction and always ignore air resistance. Okay? Always think, yep, friction's present, and always think, no, I'm not worrying about air resistance, unless it tells you to do otherwise. If it says hey, it's a frictionless surface, then you can ignore friction. If it says incorporate air resistance, then there's air resistance. How'd you do? Not too bad. Okay, step 2, pick the positive direction. Make the direction is moving positive. So to the right is positive, to the left is negative. Step 3. Determining if the sum of the forces are equal to 0. Can it be determined? And if so, is it or is it not equal to 0? And how do you know? Talk to your neighbor.
Like, I feel like it doesn't matter what side it's on. It's friction on. Okay, see, I knew that, but I was just backwards. It doesn't matter. I'll do it. Mine's like backwards. Is that okay as long as it's friction?
Nope.
It's not.
You want to do it in the way it's being forced. So, like if I was pushing you like that.
Oh, so I have the picture like this.
Yeah.
Okay.
Yeah.
That was like, okay.
Does that
Yeah.
answer that?
Um,
Okay. What do you say? Yes, no. Thumbs up, thumbs down. Not equal to 0, equal to 0. Not equal to 0, equal to 0. Okay. How do you know it's not equal to 0? Okay. Is it possible to be moving and the sum of the forces equal to 0? Yes. So don't just say it's moving. Like, ugh. Yeah, but that is inertia doing what it wants to do? No. Inertia just wants to say, I'm moving, let's just do this forever. Constant speed. This is like speeding up. Not happy. Okay? Not equal to 0. That was step 3. Step 4. Adding up your forces. Go. Keep it in mind the direction you said was positive. Okay. So hopefully you said applied force minus friction. Good. Is equal to, I don't know. All we know is it's not equal to 0. That's a little bit helpful, but not really. That just said all the possibilities from positive infinity to negative infinity, it's just not 0. Okay. So it's equal to something. We don't know what, but it's equal to some total force. It's the net force. It's equal to what those are all added up to. So we're putting this in terms of variables. That makes sense. I don't know what that value is. I just know, I'm just saying, hey, that we represent that as the sum of the forces. Now, Newton's second law says this. The net force, the total force, is equal to mass times acceleration. So I can substitute mass times acceleration in for the total force. Okay. So I can jump straight away to here. So instead of it saying net force, I can just say it is equal to mass times acceleration. Cool with that? Okay. And there, that is my setup. Okay. What does that give me? Like, why would I do that? Let's say the scenario is I'm pushing the box with 50 newtons, but there's 30 newtons of friction, and the mass of the box is 5 kilograms. What's happening to the box? Well, you have 50 newtons minus 30 newtons of friction. I got 20 newtons as my net force. Box is 5 kilograms. So you can say, hey, the box is experiencing an acceleration of 4 meters per second squared. Boom. Okay. The worksheet that I am working on that I'll publish soon, that will be due on Wednesday, will be this. Drawing free body diagrams, doing the setup, and as you get further into the worksheet, I'll start throwing numbers at you. Okay, but if you've done the setup, it shouldn't be too taxing. Sound good? Well, that's what we got.